ICTP, and he's going to talk about modular invariance and selection rules for RG flows of minimal model. Thank you.
Thank you, Rodrigo, for the presentation. I would also like to thank the organizers for the opportunity of speaking here and organizing this night conference. What I'm going to tell you about today is basically a work about the local implications of modular invariance with Horacio Cassini and Javier Magan that are here, and also Roberto Longo from Rome and Shasuke Kawashigashi from Tokyo. And if time is on my side, I will also tell you about selection rules for RG flows of minimal models. That is a follow-up paper with Horacio and Javier. So let me, before I make the main statement and the motivation, explain a little bit the setup. We will be working in Minkowski spacetime, and we will foliate that spacetime and pick a constant time Cauchy slice. Over that slice, we define a region, and we will attach a von Neumann algebra of observables to that region. One choice we can always make for this algebra, it's called the additive or local algebra, which is basically the algebra of all local gauge invariance operators that are localized inside the regions. One can formally describe this algebra as the algebra of the unions of small balls contained inside the region. One property this algebra satisfies, and also every algebra you can attach for the region, is that because local operators that space-like separated commute with each other, then it's contained in the commutant algebra of the complement of the additive algebra of the complementary region. The complementary region R prime, basically for the setup that we pick our region over Cauchy slice, is all the points that are not included in our region. They are the ones that space-like separated. And the commutant is basically all operators that commute with all operators in our algebra. This A prime of R prime contains the original algebra, of course, and also contains all possible non-local operators that are associated to these regions. When it's saturated, we have a property that's called Haack duality. That is interesting because we can think of it as a diagnose of our theory having or not having non-local operators. So let me give you some examples of how this Haack duality can be violated. The first one is regarding regions that have non-trivial homotopy group pi 0, which is basically the joint regions. And they will show violations of Haack duality for theories that are derived from a mother theory, and when we take the neutral part under some symmetry that is there. So it's like the fixed point algebra of the theory under a group. These Haack duality violations come from pairing charge and anti-charge pairs of the original group, one in each part of the disjoint region. So basically, if we pair those of these operators inside the same ball, we can construct them additively inside the ball, but if we put it in separated regions, it's not contained in the additive algebra of the separated balls, but because it commutes with everything that is outside, it can be associated to the region. The second example that appear in regions with non-trivial homotopy pi k is basically in theories with k-form symmetries. A typical example would be regions with non-trivial pi 1, like torus regions, in 4 dimensions with non-contractible Wilson loops. So the main idea I would like to try to convey here is that when Haack duality is saturated for the local algebras, it means that we have enough charges to break all these non-local operators into local ones. I will call this property completeness, as it can be understood as some sort of spectrum completeness of the theory. I would like to highlight 2 things. The first one is that this definition is very precise. And the second one is that there's nothing wrong about the theory being non-complete. For example, Maxwell fields are not complete, and it's because they have a one-form symmetry with non-trivial Wilson loops and so on. And there's nothing wrong with them, it's just what it is. So then what I want to talk about today is basically asking what is the imprint of these non-local operators over the bootstrap data of the CFT. And what I will try to argue is that this completeness in 2D CFTs is the same as modular invariance. Modular invariance understood as symmetry of the toru partition function under Moebius transformations. So this will give us a local interpretation of modular invariance. So what's this implication of modular invariance over the local algebras? And also can be easily generalized to any space-time dimensions. One question that might arise is, well, but I have been living in 2 CFTs with modular invariance models a long time. Why should I care about these non-modular invariant models? And what I will try to argue in the second part is that they are useful to develop selection rules for RG flows. In particular, I will show you the example of minimal models. Okay, so because we're going to talk about 2 dimensions, let me be a little bit more precise about how Hug duality violations look like. The first thing is that these non-trivial topologies of pi k, with k being 1 or greater, are not allowed. Basically, we only have the pi 0 case with our 2 disjoint intervals. And the Hug duality violations come from pairing these charge-anti-charge operators that are labeled by the representations of the group in principle, and an index associated to that. In the case of the group, in higher dimensions, in the complementary region, there are also other Hug duality violations that are called twists and are labeled by the group itself. And in this 2-dimensional case, because of topology, they also can be associated to the same interval. So in this case, we have these 2 types of violations appearing at the same time for our region. It's the same thing that happens in 4 dimensions for instance, the Maxwell field, or in any gauge theory, that the Wilson and the Toff loops have the same codimension. The second thing is that these charge operators satisfy an OPE like decomposition like this, where now these n matrices do not need to correspond to the fusion algebra of some group. It can be something more general. This basically to accommodate for the presence of non-invertible symmetries. What I will try to argue is that in a 2D CFT, the absence of these sectors basically implies modular invariance. So let me be a little bit more precise about how modular invariance can be violated. So one thing I would like to also highlight is that the algebras I will be talking about are algebra defined over regions in Minkowski spacetime or in the cylinder, but not on the torus. This is basically an imprint of the torus partition function of the local algebras in Minkowski spacetime. But modular invariance is usually split in 2 parts. The first is T transformations that take the modular parameter of the partition function tau to tau plus 1, and the partition function is invariant under that. That for us will be a necessary condition because basically implies self-locality of the fields. There is a proof by Reren in the 2000 of this. And well, also this condition of self-locality implies basically that we are picking the right pairing of left and right chiral representations to have the appropriate spin, integer of Halley integer spin. This is required because we want our Euclidean correlation functions to be to not have branch cuts, basically. And the second part of modular invariance, that is invariance under S transformations of tau going to tau over tau, is what's going to be the same thing as completeness, this completeness notion I defined before. And this is basically not a minimal requirement for a CFT, or I will try to argue that. And what, yeah. In principle, both. No, I accounting for the minus sign also. Okay, this is for, yeah. But yeah, okay. So well, what I want to show you next is a proof of this statement using a physical proof using quantum information measures. So the key element of the proof is basically understanding that Renyi entropies are able to probe Hug duality. So what a Renyi entropy is, basically, is the logarithm of the trace of the density matrix, the reduced density matrix of the region elevated to the n. and it can be computed via the replica trick, where we replicate the manifold n times, and then glue together the boundaries of the region. And basically, this trace of rho to the n is the coefficients between the replicated manifold partition function and the original partition function elevated to the n. And for the single interval case, for a CFT, family gives you this result, which is basically that the range isentropies grow as the log of the dimension of the region, with the central charge as a coefficient before. So now, in this setup, when we have a global pure state, then the entropy is the same for algebras that commute. So basically, the entropy associated to the additive algebra of a region will be the same as the commutant of the additive algebra of that regions. This, in principle, we don't know if it is or not the algebra we are associating to the complementary region. We only know it's the commutant of this one. In the case that Haack duality is satisfied, there is not a choice for this. Then, because we have this, the entropy of our region is the same as the entropy of the complementary region. And this relation can be think about a diagnosis of if Haack duality holds or does not hold. Okay, that was like the key idea, but to make a relation with the partition function of the torus, we have to do something a little bit more fancy, which is basically look to the mutual information. The mutual information between two interval regions that are bounded basically by these A and B's. And it's the sum of the range entropies minus the entropy of the union. And it is known to be solely a function of the conformal cross ratio defined by these A's and B's in this way. And this has this function that we will be extracting, and we will be interested in just this part U. So from the properties that the range entropy is satisfied when Haack duality is satisfied, that basically for complementary regions they are the same. Here it can be seen by changing x to 1 minus x. We have that these U's will be the same in the case that Haack duality holds. So a good measure of Haack duality is this crossing asymmetry that we define basically by the difference between these two U's. So the bottom line is that when this quantity is 0, then Haack duality holds, and when it's not 0, it does not hold. Okay, but how do we compute this asymmetry or these range mutual informations? Well, there is a well-known conformal map from the replica manifold for the n copies and big N intervals to the higher genus partition function of n minus 1 times n big N minus 1, which basically gives us a mapping of the calculation of the range entropies to the higher genus partition functions. Yeah. Which one? The previous one? This? Yes, are if unknown leaves. Okay, so basically for the two interval case, if we pick n being 2, we basically have this replica manifold, and then it can be mapped to the torus partition function. This was computed by Hedrick in 2010, and it's basically this result, where the logarithm of the torus partition function enter this mutual information with a modular parameter defined through the conformal cross ratio like this. When one tries to see how this mutual information enters this asymmetry we defined before, we basically get this equality. Basically, this A2 is the logarithm of the coefficient of the partition function of the torus and the S-transform partition function of the torus. This condition can also be generalized to higher n. I will not tell you that, but here at the partition functions of a higher genus Riemann surface appear. A2 is basically the difference is, yes. The previous slide. Yes, it's basically the difference between U's that appear in the mutual information like this. So basically, you can think about it heuristically as the difference between mutual informations with the cross ratio x and 1 minus x. Okay, so well, there is a thing with twist fields. You mean the replica twists? Well, when you don't have modular invariance, in principle, your theory has these non-local sectors. So you cannot compute the Renzi entropies. You can compute it through the twist, but the twist is something that is non-local in the sense that it belongs to all the region and not only for the extremes of the region. So it's not so easy to understand the calculation in terms of twist partition functions and twist expectation values. In principle, any 2D CFT, posonic. Okay. Yes, yes. Basically, so I can be a little bit more precise on what I mean by generalized to higher n in the next slide. But basically, you can get the AN here, and then here a coefficient of higher genus partition functions with one particular modular transformation. It's not a generic one, but it's basically because this modular parameter of higher genus will only be defined through the cross ratio. So it's a particular transformation. It's not a generic one. Okay, so because this asymmetry is maybe a little bit difficult to calculate in examples, let me study some limit of it. We will study the high temperature limit of the partition functions, or which is the same thing as the near interval limit of the mutual informations. Basically, the torus partition function you can write in terms of chiral characters like this, with this m being natural numbers. And we know that the S transformations over the chiral characters act like this with a modular S matrix. And this modular S matrix defines the quantum dimensions of the representations like this. Basically, it's this coefficient between S0 hour and S0, 0. And then in the high temperature limit, one can prove that the coefficient between tau and the S transform one has this shape in terms of quantum dimensions of the models. And of course, the same thing appears in the near interval limit of the crossing asymmetry. Well, from the definition of tau in terms of x, one can check that tau going to 0 is the same as x going to 1. This particular number here, that is the same one, it's known in the algebraic quantum field theory community as a global Jones index. What this means is basically these Jones index are a quantity that is defined for any inclusion of algebras. So you have an algebra inside another one. I can define this index that is a measure of the relative size of one inside the other. And in this case, we will be looking to the inclusion of the algebra of the union of the regions inside inside the commutant of the algebra of the complementary region. This Jones index, well, then will be basically a measure of the relative dimension between these two things. And one can see that it's related to the category of the char Doppler-Hag-Roberts superselection sectors. Basically, these sectors are endomorphisms that keep our local algebras invariant and define a category. And it can be obtained through the sum of dimensions of that category, this index. To give intuition, for finite group, this is basically G squared. And when Hag duality holds, then the inclusion is trivial, and this mu is equal to 1. To go back to your question, basically, if you do the same thing with higher genus and take this limit, you always get the same mu. It's not that this mu is something that you can relate to the genus of the surface, but basically it's always the same one. Okay, so let me give you a little bit of summary of what I have said till now. Basically, we have this crossing asymmetry that is defined through a difference of mutual informations. And in the near interval limit, it coincides with the high temperature limit of the partition function, of the partition function over the S-transform partition function. And in that limit, this global index appears that can be computed through the dimensions of the category of DHR sectors or through the quantum dimensions of the representations of the Virasoro algebra that I include in my model. Also, there are 4 statements that are equivalent. The first one is that the theory is modular invariant. The second one is that it's complete in the sense of duality, that the algebra of my region is the additive algebra of my region is the commutant of the additive algebra of the complementary region, that this global index is 1, and that the theory has only the trivial superselection vector, basically that this category is trivial. So some examples. The first, yeah. Sorry, it's again?
So I'm saying that in 2 dimensions, S is not enough. You also need to demand invariance of the one-puncture torus. Not the torus, but torus with one puncture. That's clear that the poor cyber showed.
Why?
He's telling about higher modular invariance.
You want to write down what the conditions are, so that one way of saying it is the correlation function does not depend on the choice of the OPE channel.
Yes.
They showed that you also have to consider the constraints that come from the one-puncture torus. Here you were talking about just the torus with the insertion. So I'm asking, adding the constraint of the one-puncture torus, does it give you... Sorry?
No.
For this story about the MUG or whatever.
All of this depends only on single torus.
Yes.
So you're saying that if these conditions are satisfied, what I'm confused is that if these conditions are satisfied for only imposing modular invariance, then what other conditions does the one-puncture torus give you?
Yes, in principle.
In the usual context, it gives you more constraints than just the torus.
Yes, in principle, you can have more constraint on the algebras than it being complete. Also, what I mean is that this S-duality of the torus is enough for it to be a complete. But maybe there is more constraint that mean other things. Yes, yes, probably that's true, but I don't know what that information is.
One comment on that is that this completeness of intervals gives completeness of any interval. So completeness is completely complete.
Well, basically, that's you can also see for the higher Chinus partition function, instead of changing little n the range index, big N the number of intervals. You can see that statement Horacio says is true. Okay, so the first example, we take the central charge to be 1/2. Then what we'll study is basically the Ising CFT and the subalgebras of the Ising CFT. We have, in principle, 3 chiral representations. The identity, the epsilon that in the Ising is called the energy, has scaling dimension 1/2, and then the sigma that has scaling dimension 1/16, spin operator, and satisfy these fusion rules. So a question one can ask is, well, if I take bosonic spin 0 fields, basically I do all the diagonal pairings, which allow the possible close of algebras I can do with these chiral representations. And it turns out that there are 3 of them. The trivial one is basically the Ising CFT. You include all fields. This is a complete theory. You can check that the global index is 1. And then there is the C2 orbifold, which basically kills the sigma. When I say orbifold, I mean only the neutral part. I'm not lifting any twisted sectors, just taking the neutral part under the group. And this has mu4, which is basically G squared for C2. And the third one is including only the stress tensor or the identity sector, which gives you mu16. And one can see that it corresponds to a DHR category SU2 level 2. Well, a couple of comments. The first one is that this model one can also complete to the free fermion theory. one can do it. I'm not showing it, but it's fine. And the second one is that these shown indices are known to take only some allowed values. For instance, this mu has to be 4 cosine pi over n squared for n going from 3 or greater, or it has to be greater than 16. And one can check if you pick wrong choices of algebras that have problems or models that have problems, then the shown index doesn't fall in these allowed values. For instance, if one picks 1 and sigma, that's not closed under fusion, so it basically does not define a good algebra. And we get this value 16 over 9, which is not included in this list. So I think that's fun. I don't know if useful, but yes. So there are two. Originally, what Sean's proof is basically for the square root of this, but well, one can define another index that is the index defined by the inclusion of my algebra of a single region in the complete model, and it can be proven that this is the square of that. So because that's an index, it has to satisfy this with a 4 here, and because the square, it goes to 16. No. It's this series, yes. It's discrete with this series, and then it becomes 16.
Sorry, I'm asking a really dumb question. That thing asymptotes at 4, the left-hand side asymptotes at 4.
So there is nothing between 4 and 16, yes. I think that's true, yes.
Because normally the thing that appears is 2 cosine pi over n.
Yes. Yes, this is that square. I think it's square here, and this is 4, but maybe it's a typo, I don't know. Okay, so another example that is a little bit different is cases where this index is infinite. It doesn't always have to be a finite one. So now I will look to a theories with central charge equals to 1 and take the neutral part under a continuous group. Basically, in this case, one can show that this asymmetry for n equals to 2 diverges as a log-log, with the coefficient being related to the dimension of the Lie algebra. One example one can see this is true is the free chiral scalar with partition function 1 over eta. This is not modular invariant. And if one checks how this goes into the asymmetry, basically diverges 1/2 log-log. This 1/2, or this 1 mainly, is because this theory of the free chiral scalar is the same theory through bosonization as the fermion current. So we can think this as we are taking the neutral part under the U1 symmetry of the fermion. And the second example is the Virasoro net, basically only including the stress tensor. We know the character, so we know the partition function, and we see that the free appears here. So why is that free there? Basically because the Virasoro algebra, the Virasoro net for c equals to 1 is the SU2 fixed point algebra of a SU21 Wessumino-Witten model. This is related to the original story from diagraph Berlinde, and it has been formally proved by Reren later. Good. So this sort of concludes the first part of the talk. The second one, I will try to convince you that this has a useful application, that it will be to develop selection rules for RC flows, and I will especially apply it to minimal models. For that, first of all, I will try to make a classification of all non-modular invariant minimal models, or all subalgebras of modular invariant minimal models, and then I will tell you what the selection rule is and what it gives us. So to review briefly, a minimal model, we will take them to be unitary, then it has central charge less than 1, and it's labeled by a unique integer number m that is 3 or higher. And well, it's basically this. And the chiral representations are known, have these scaling dimensions, and are labeled by two numbers, R and S. R is an integer number that goes from 1 to m minus 1, and S goes from 1 to m. And, well, the chiral fusion rules are also known. You can derive this very easily from you can compute the S matrix of the characters and then apply Berlin the formula, and you get this. But, well, so then one would like to write the torus partition function for this. This is basically the same as before. It's the sum over the characters, pairing the chiral and the left and right chiral parts. But the good question is, how do we get a modular invariant model? This has been solved a long time ago. It's called the ADA classification. But one possibility is to include all spin zero fields that are allowed. And this gives us this partition function. This is known as the AA series minimal models. This one half here only accounts for the fact that the representations have a symmetry. RS is the same as m minus r, m plus 1 minus s. But the question we would like to ask is, well, how many subalgebras these minimal models have? And although the number of distinct fields grow like m squared, it's found that one can always find, for m greater or equal than 5, 8 closed models. So this is basically the 8 of them. This graph, the one on top, is basically the modular invariant model. And here below, we have only the identity sector. It's always closed. And then, for example, we know that all these models of the AA series have a C2 symmetry that basically transform the fields that have even R with a minus sign. So if we take the neutral part under that symmetry, we get this algebra here. There are also other things. For example, if we take R being 1 and S being any odd number, that closes an algebra. And this one here that has category SU2 m minus 1. And one can play that game with a lot of things, and you get this. All these global indexes are known, are basically here written in terms of the global index associated with the SU2 m minus 2 category. But, well, it is what it is. This graph is for an odd m. For even m, we get the same result. Only the categories are shuffled around the graph, but basically are the same categories. So what happens in a more general case? So these IDA classifications tell us that if we take these diagonal minimal models and they gauge the C2 symmetry, and now we add the twisted sectors, then we fall in another modular invariant model that is one of the AD or DA series. In this case, for m being 4m plus 2 or m being 4m plus 1, we get another 8 extra submodels. And for m being 4n or 4n minus 1, we get only 2. For the E series that depend on the exotic groups, X6, X8, A7, and E8, we can do it, and we get for E6 basically that to be unitary is known as m has to be 11 or 12. So we can compute that here you have other extra 6 algebras. And just a couple of comments about this. The first one is that to make this computation, one needs to know the non-chiral fusion rules. For the AD series, this is very easy because one can get them from the chiral fusion rules and the conservation of diagonality. And from the E series, it's a little bit more involved. There is a very recent paper of Universitat and Ribault that they compute these fusion rules through the bootstrap. So that's what we use to derive these things. Yes? Yes. That's basically what it is, yes. So in principle, you should be able to find for these algebras a subset of Berlin the lines. And when you take or projectors, that when we take the neutral part under the action of those lines or projectors, then you get these things. Yes, yes. So I'm taking this approach that might seem a little bit less usual, basically because it's very simple. Like you take the fusion rules, you put it in the computer, and you see what the close sets are. The second clarification is that there was a classification of possible tensor categories that is well known since 2004 from Kawashigashi and Longo. Our results are consistent with them. They have some difference in the sense that they are classifying categories, not models. So we have sometimes two models with the same category, but it's coarse-grainingly consistent. Okay, well, this is an example. This is m equals 11. We have the AA series, the AD, and also one of the exotic ones. And this is the kind of graph one gets. So, okay. So now how we use this thing to understand RC flows and make some feel useful out of it. So what we want to do is to take now I'm talking about generic CFTs, not minimal models. Take a CFT in the UV and deform it with the relevant operator of the UV and try to develop some selection rules of the CFTs we can find in the infrared. So in the general case, one can in principle have other things in the infrared. You can study completely gap or have some gap phase and a CFT on top. But we are trying to say things only about the CFT in the case that doesn't appear any gap phase. So the key point is that one can consider this flow happening inside the minimal possible model that contains this deformation. So basically, that's the model generated by this field and the stress tensor. And then, well, in the case that the RC flow is not massive and it doesn't develop IR emergent symmetries, then the selection rules we propose are these ones, basically that this global Jones index is preserved along the RC flow, and all of the indices on top of either one of this node, basically, so this is one of the squares, everything is on top, is also preserved, and the category of the HR sectors is preserved, and also the categories on top. And the structure of possible completions is also preserved. Well, this is what I said before. We expect this to be like a general thing in the case that you don't have the massive phase and so on. But I will show you now how this applies to minimal models. So there is a well-known example about RC flows between minimal models. It's due to Samoloishikov in the 87. One basically takes a minimal model in the UV with m of the UV being m plus 1 and deform it by the less relevant operator, that is this phi-1 of the UV. And one can check, perturbatively computing the beta function, that in the infrared you have also a minimal model that has m in the infrared being m, so basically decreases by 1. So how we can make this work from our selection rules? So basically, we take this field, phi-1 and try to see what is the smallest algebra that this phi-1 closes also with the identity sector. This is basically the one I told you before. So it's phi with r being 1 and s being any odd number. This is a representation of the CAC table of how this algebra would look like because it's a diagonal one. So basically, we're including all these odd S representations. And this big line in the middle is basically all representation that have scaling dimension less than 1. So it's basically what will be, when we couple them together, the relevant operators. And this algebra has only one, that is phi-1 so the category associated to this algebra, the HR, is SU2 level m-1. Or MUV minus 2. And we would like to find the same category in the infrared. That is doable, and it's basically correspond to this model, which is for m, so decreasing 1 in m, all the fields that have r equal s of the UV and s fixed to 1. So in the CAC table is this thing. Okay, so we find the category. What I also told you is that all the categories on top and all the indices on top have to be preserved. So this is an example of how this works. In the case that m of the UV is 4n plus 1, so this is one of the, this is the completion of diagonal, and this is the completion of the AD series. What I told you is that the structure above needs to be preserved, but the structure below, we didn't say anything about it. And what is very funny is that when we want to see what will be the IR fixed point, so it's decreasing this by 1, basically that's what's happened. All the structure below is erased, and all the structure on top is maintained. And well, this is one example of this. So, of course, this RC flow generated by this phi-1 is not new. It's well known in the literature. So what else these selection rules include in itself? What else can we obtain with them? So the first thing is that it generalizes some RC flows that were known for some specific minimal models to the complete tower of minimal models. So basically, one example of this is the deformation between the 1-2 field. This, at least to my knowledge, was first seen in this paper by Lastic, Musardo, and Cardi, where they compute this flow from using this field from the tricritical icing to the icing. And this basically can be derived from our selection rules by the conservation of this category, SU2 even m-1, for all minimal models that go from m to m-1. It has also appeared the same RC flow in this recent paper by Tanaka and Nakayama of last year that is more or less at the same time our paper. The second thing is that one can also use this to develop RC flows between non-linear, non-diagonal minimal models. One nice example of this is a model from the E6 series. You can see that they can have an IR fixed point, that is the tricritical icing or the icing, by the conservation of this SU2 category. And there's also a paper of Nakayama of 2023 that talks about this SU2 category appearing in both models, basically as a category of fusion of Berlin lines. So following of what Paul was saying, it's basically a similar statement. And the last thing is that once one can identify one of these RC flows, and we know the category of DHR sectors, then basically one can try to identify these endomorphisms of the DHR category in terms of fields. And once one is able to do that, you can get a mapping of fields in the infrared to fields in the IR. So this is what it gives you for the 1-3 case. And it's basically consistent with what Samoloshikov originally proposed and also Gayotto derived in 2012. Okay. So to finish, to give you a conclusion and outlook of what I said today, in a 2D CFT, I argue that completeness is the same thing as modular invariance, and that this completeness can be measured through this quantity, it's called the global index. The closest the global index is to 1, the more complete is the theory. And this global index can be seen to appear in this asymmetry defined through difference of mutual informations in the near interval limit, or by the torus partition function using this coefficient with the S transformation in the high temperature limit. This global index and the DHR category can be used to develop RC flows, selection rules for RC flows when we study these non-modular invariant models that basically allow us to rederive everything that was known about RC flows of minimal models between minimal models mainly. And well, the question now is, what can we learn from this setup in more complicated RC flows? What can this teach us about gap phases or higher dimensions? So for the case of gap phases, we expect that some of these will be true. So the structure will not be totally preserved, but some of the structure will be preserved along the flow, and then some of it will be erased and fall into the gap part. For higher dimensions, the story is a little bit different, in the sense that we were talking today only about pi0 violations. This is disjoint regions. But in higher dimensions, we have other non-trivial regions with other kind of actuality violations coming from higher front symmetries, for example. So one has also take that into account for the selection rules. And for the pi 0 case, well, one had, in principle, these pi 0 DHR sectors only come from groups. So it's a little bit more difficult to develop useful selection rules from them. And that's basically all.
Okay, so we have 15 minutes for questions, so please go ahead.
Paul.
Okay, John. Okay, Paul.
Struggled to identify some analog or modular invariance for us. I guess one reason you might want to do it is because it relates the low energy spectrum and the high energy spectrum. Can you use completeness to figure out what it should be?
Well, a bit of the argument we were trying to make is that once you understand this relation in 2 dimensions, that modular invariance is the same as completeness, at least over the local algebras, then basically this completeness statement generalized to any dimension. The question is that if you can do that from some modular invariance in higher dimensions, I don't have an answer. I would expect that probably come from some constraint over the modular space of the theory or something like that. But it's only an idea, it's not.
So, did you use unitarity in any important way? Because it looks like, what, at least it did seem to me, so you could do all this through non-unitary methodology, which has all these.
Yes. In principle, so these algebras you can compute from non-unitary minimal models. You can see that they are the closed algebras. It's basically the same for diagonal, at least the same 8 algebras. And if you try to follow that direction strictly, you end up from this Nakashima paper that also talks about RC flows between non-unitary minimal models. We don't talk much about that because, well, I'm not sure about all this DHR story for non-unitary minimal models. It's not that it doesn't hold, it's just I don't know how it works. But basically, this matching between sectors you should be able to do it. No, I think it's true. I think that's true. Yeah. Sorry. Well, we are a little bit using it in some sense. But in principle, once you know these, the fusion rules, the chiral or non-chiral fusion rules, you can plug this in the computer and it will give you all possible subalgebras. One of the ones that is included is the modular invariant one. And you can check that it's modular invariant. So in that sense, you can derive it. But in practice, we're a little bit using it. Yes, the process ends there. So you cannot, like say, overcomplete your model. One manifestation of that is that these Jones things start being less than 1, and that's not allowed. These global indices. So. I don't have one. I don't know if someone has.
So wait, so it's a classical, so the Jones index is defined anytime you have an inversion.
Yes.